So very good afternoon to you. We have this quantitative research course session. In this session, my plan is that we do some data analysis with the help of SPSS first. And as the need be, we'll be discussing some concepts, but in the context of the analysis. And as you all have done that, you have typed in SPSS in the search window and you are able to reach at this spreadsheet looking shape, looking picture, screen, whatever. And here you can see the phrase var. It's an abbreviation of the phrase variable, because here we will be having our variables, okay? Many people do in different way, but normally I'm an old-fashioned person. I still love Excel. So all my data is saved in Excel. But from Excel, I can simply move data to SPSS workspace without any hiccup. It goes very straightforward. The file which we shall be working on is this one. This is the variable. And you can see that there is some additional information, but don't worry about it. This is the data which we shall be using. You can see here that there is a fictitious study. I'm imagining that there's one researcher who is going to study that on what factors the crime rate depends. So it's a quantitative research, but done by somebody, hypothetically. And the study title of this thesis is that what are the determinants of crime rate in a city? And this person has taken some variables. This person measured crime rate, dropout in density, which means that the students, that fraction of students who are not able to complete the studies. So they join the school and they leave it and they don't complete the degree. The idea, the theory behind the dropout density could be that in a system, in a culture, in a city, where we have a larger percentage of people who drop out, the crime rate is likely to be more. And who tells us this thing? Literature. So this is why it's very important that you are able to go through the literature, and from the literature, you form, you reform, you adapt some ideas which you are going to apply in your real data. This is why it was very important to discuss hypothesis last time when we met. Another variable which we could see is a poverty ratio. There is a popular belief, or there are some studies also that those places where people are relatively poorer, the crime rate is more. Again, this comes from theory, literature. Alcohol consumption. We expect that this variable would be having a positive, not in the strict sense, but is positively correlated with the more alcohol consumption, more crime rate, right? Young age people, those cities, those habitats where there are young people relatively more, the crime rate is also expected to be more. I mean, imagine a city where the young population is very frictional. The population is mainly comprising of very old people, middle-aged old people, or kids, right? The crime rate will be low, But that population between the age group of, let's say, 15, 16, 17 until 30, 35 is that population, right? So just maybe some researcher have found in his study that it's not just the high population, more population, which makes more crime rate, which supports more crime rate, which can cause more crime rate, but also the composition of population is very important. Demographic feature, okay? Working population, another variable. Look, I just cooked up this. Basically, this spreadsheet is a finance spreadsheet. But what I did, I changed the name of the variable so that we can get it in a better way, right? working population, we expect that those cities where people are working, what do you expect if there's a city comprising of more working population, the crime rate to be? No, because they are so busy in their things that they don't have. Education intensity, this variable I cooked up, assuming that there is a network of schools and other educational institutions in the city. So higher education intensity, lower is the crime rate to be expected, right? Number of cops. So I thought that maybe the law and order situation should also be considered, that those places where the police is large, maybe the crime rate is less. That's what we expect, that hey, the theft took place and there was nobody to catch. We often complain. There was a bank robbery yesterday. There was only one guard, nothing else, and he was also unarmed, and there was no real cops who could chase. There's one way of thinking. Of course, there can be, for all these variables, you can also be having the alternative arguments also.
At the reality, and you look at the places where you have the most calls.
Oh yeah.
You also have the most crime.
But then you have to see this way. Is the phenomenon of having more cops a cause or an effect? Because if a city is having lots of crime rate, and as an outcome of more crime rate, the cops have come, then exactly that argument would apply, which you are saying, right? So here, the crime rate is a cause, and the police personnel is an effect. You see, but what I'm saying is that if we expect more cops available in a city, we expect that the crime rate to be lower. So we also have to model the whole thing, the way we are going to deal with it, right? And again, all these things, they come from literature. And time and again, I'm underlying the importance of literature review.
From these results and decide which elements.
You mean the actual real thesis, if you're doing?
Yeah.
It's difficult to say. I think we expect that you cover as much as you can. Of course, you can't cover everything. So for the literature review, it's difficult to say, but of course, the relevant literature is very important. Look, in some cases, the topic is so well known, right? Or that there's a literature is available. So then we expect you do a lot of lit review. But in some studies, the topic is so new, so novel that maybe it's difficult to find the literature on that topic. So then we get some transferable literature from here and there, some, like, for example, you're studying this thesis, you're writing this thesis in the context of sociology, right? But maybe this topic is so new that there is not enough evidence. Then you can get some ideas from psychology. You can also get some idea from law faculty. You can also get some idea from, let's say, demography, economics, because economics, yeah. You can also, so you can get the ideas or the literature from multiple sources. But if you really want me to give a number for my IB thesis, I'm a kind of person who really push students to have more references because I believe that like reading, like writing. In other words, if you don't study much, if you don't do enough literature review, I don't expect that the student would be producing any miraculous thing, that he has some divine. It has to go from the way you study the articles, the literature. And it may include books, it may include the scientific articles, or it can also include some reports or some other documents. I'm very unhappy if my IB students have a list of references less than 7 to 8 pages in the thesis. Usually I push them. I shouldn't force them. But anyway, I do it. I really push them that they should be having at least 7 to 8 pages of references. And most of them should be scientific articles. Periodicity of scientific article is very important. Some people say that no, always have the latest articles. I don't believe in it, because if there are some masterpieces written in 1930s, take them, right? Look, in majority of the scientific articles, empirical studies, they are still using those theories which are used in the past. So basically, they are also the practitioners of those legendary theories. Then why don't we use them directly? Why don't we consult them directly and see the original article? For example, in my literature, in my empirical research, I used a lot of agency theory. But I would say that if somebody wants to study agency theory, why should they read my article? I'm also like that student. I'm just using the agency theory. Go and read the original text, which was published in 1936. So that makes it even more important than my own study. But for the empirical evidences, because when you do the literature review, you also need to understand that you start with some conceptual things. And then slowly you spread to the empirical evidences. Yes, empirical evidences can be new, can be latest, but if you really want to quote and you really want to dig deep, those theoretical, conceptual part, then it's not a bad idea to consult the original articles, which no matter when they were published. So that could be a good way to do. Yeah. Right. So again, as I said, that all these thoughts, all these ideas, they come from literature, and you finally write them in the form of hypothesis, right? And then number of COPs and population density. Then I also take this variable that, okay, all right, let's take the, for example, I must be struggling when, even though it's a very fictitious exercise, but I would say that as a researcher who is still doing the lit review, I would have been struggling. Should I take a traditional variable called population density, which many people have taken? Or should I take this, this variable, which shows that what percentage of young people is there in the population? And I took both. Why? Because I want to see that in this context, in the context of my study, is the more relatively new variable, which some researcher have just done it some maybe 4 or 5 years ago. Should I take that one? Is that more applicable in my empirical analysis? Or is it so that I should stick with the old traditional tried and trusted variable like population density? So it could be possible. You might find more than one variable which represent the same phenomenon. And you want to see that which of these, the phenomenon is same, the population, right? But do you want to see the overall population, or is it so that you want to see that, you know what, we know from the common sense, we also know from the literature that the young kids will not, you know, stab anybody, and very unlikely that even the elderly people would do it. So let's take that population, which is a young, so-called young population, right? So there can be alternative opinions also. Anyways, so this is our data, and let's say that this student may be writing PhD thesis, and he took the data of about 551 cities or provinces, whatever. So the unit of analysis, assumingly in this case, is the city. Okay. Now, this is a typical case of cross-section study. The cross-section study is when there are different subjects and objects, respondents, who are providing us the data, or who we collect the data from, whether primary or secondary, but the year of analysis is, the period is same. That is called cross-section study. So it could be possible that this guy, this researcher decided that, you know what, I'm going to take this period 2018 to 20. So I would try to approach the local council of these 500 plus cities, that what is the latest data available with them for this study. And then I collect all the variables from there. Then this is called cross-section, but you can also have a study called time series study. The time series is that you are studying the crime, how the crime rate is affected by different determinants in the same city over multiple periods. Like, for example, you can have the crime rate data yearly of New York for the last 100 years. And similarly, you would also take what was the poverty ratio that year, 100 years ago, right? Similarly, what was the working population now till 100 years ago? So you are studying one place, one the unit of analysis over multiple periods. In the cross section, the period is same or more or less same, but you have the multiple respondents. In this case, I can't say this thing. This study, this hypothetical study, sorry, just a sec. So this study will be called a cross-section study if the period of analysis is same. And I can do this way, that let's say that this is the data of New York. This is the data of London, let's say, and so on and so forth. But the period is more or less same. I'm saying more or less same. Sometimes you have to be a little bit lax, that you want to take the latest data of all these variables, but could be possible that in case of New York, the data is published even for 21, but you don't have the data of 21 for London. So then you might have to take 2020 data, right? But it's more or less same. But the thing is that the respondents, the subjects, the objects, they are changing. Next could be Paris. Next could be, for example, Tokyo or Helsinki. So this is called a cross-section study, right? But this will be called, so the time period could be yearly, monthly, that remains same. That doesn't change. The periodicity of getting the data doesn't change. You don't get the multiple periods, but you get the multiple objects or subjects, right? On the other hand, this will be called a time series studies if I'm only analyzing, let's say, New York, and this data belongs to multiple period. Let's say the first observation is year 22, last quarter, fourth quarter. I can say Q4. I can't say 520 years, but that is why I'm not calling it annual. So I'm calling it quarterly data. Quarter means 3 months, so 4 quarters a year. So if the 500 observation, I can assume that somebody is studying for the last 125 years data, which is doable, so I can call it Q4. New York 22, third quarter, and so on and so forth. So here there's no Paris, there is no Helsinki, there's no London, it's all New York for the multiple periods. Then this study would become a time series study. Mhm.
What if we want to study?
You can do it. You can do it. Then it's called, if you also, let's say, very good question. This is New York. This is also New York, right? Oh, sorry. '22. Oops. This is second quarter. Let's call it second quarter. Again, New York. 22. First quarter. New York. Okay, now 22. Fourth quarter. London. 22. Third quarter. London. 22. Second quarter, London, and so on. Now here, what you see, you have the multiple periods, and you also have the multiple respondents, subjects, objects. Why I'm saying subjects? Because when you are contacting the non-living people, it's a subject. But when you could also get some data from by interviewing people, then it's a subject. Then it's a subject. But when you're getting from the data from a city, which is a non-living thing, even though it's a living thing, but not like a human being, not like the breathing and stuff, then we call it object. So when you are having the data from the multiple respondents for the multiple periods, it is called pooled data. We call it pooled. I can write it down. Pooled data. Yeah, or we also call it panel data. Some people call it pooled, some call it panel data. Okay. So you can call it pooled data, which involve the characteristics of both time series and cross section. Let me check. Did I delete it? Here we go. Yeah. So this could be pool data or panel data, right? Make sense? So when you have the same period and multiple respondents, it's called cross section. When you have the same respondent but multiple periods, it's time series. But when you have exactly when you have the multiple periods and multiple respondents, then it's called pool data. Now the pool data or the panel data could be balanced or unbalanced. That's a very good question you asked. Now I can tell you more. Balanced pool data and unbalanced pool data. Balanced pool data is, let's say you have total 400 observations, right? 400 observations. You have 4 quarters. 4 quarters. And you have all the 4 quarters data from 100 cities. You get my point? No data is missing. So you have exactly balanced data. In other words, you wanted to analyze 100 cities on quarterly basis, and you have the quarterly data also available for each city. Then you call it balanced pool data or balanced panel data. But there can be a situation. There can be a situation. Let's say for the year 22, that is the latest year you can get the data, even hypothetically. For New York, all the 4 quarters are available. So all the data for each quarter, each of the 4 quarters is available, and you take them. But the problem happen is that for London, the data of 22 last quarter is not published. Should you exclude London from the study? No, because maybe your research topic is that you want to study this whole phenomenon in case of the largest cities in the world. And if your study, London is not included, then your data is biased. It lacks its reliability. It's not very, the legitimacy of your study can be questioned. But the problem is that you have to satisfy yourself with only 3 quarters of London's data for 22. Take it, no problem. For the New York, you're writing 4 rows. For London, 22, you're writing 3 rows. The problem becomes even worse when it comes to Tokyo. They don't have data for the last 6 months. So you only take 2 rows, the first quarter for Tokyo and the second quarter for Tokyo. So what you're doing is that your data is a little bit unbalanced now. But because you're going to make it a very big comprehensive study, you say, all right, no problem, we can compromise, but if something is better than nothing, let's take the data of first quarter and the second quarter of Tokyo. It could be possible that you also include Manila in your study. And Manila, the latest data is available for 21. So nothing, no first quarter, no second quarter, third quarter, fourth quarter for 22 for Manila. Then you have to stop at Manila at the end of fourth quarter. Take it. So you just put it, so create the row. So it means that for 22 data, Manila is not featuring anywhere, even though Manila is in the study. In that case, your panel is unbalanced pool data or unbalanced panel data. Make sense? So this is where the data sometimes can have an impact on, rather than the concept, but it's a reality. We live with it. We can't escape it. The availability is like, even in the qualitative research, it could be possible that you have planned that you will be interviewing 5 CEOs of the companies, and then what happened is that the 2 CEOs they decline and you can't find any other CEO. Then you may have to adjust with interviewing 2 CFOs or 1 CFO and 1 CMO, even though they represent the company, but they don't know as much as the CEO knows. So again, the data can influence your analysis and findings, be it a quantitative study or a qualitative or quantitative, whatever. It can have an impact. All right. So we have this data now. We have these variables. We have the crime rate, we have dropout density, we have the poverty ratio. So all those variables which can have an impact on the crime rate in the city. And as a researcher, you have decided to do quantitative research. Okay, give the reasoning for it in your methodology chapter. You want to study the cities, big cities in the world. Okay, give a justification that you are collecting the data, from where are you collecting the data, what period you are studying, so on and so forth. And then you have your spreadsheet ready. Okay. And what you can do is, you can simply select the data, just copy it, and then you go to SPSS workspace. I need to delete it. Here. And then you go to the empty space. And here in the first row, first column, if you click right, if you give the option paste with variable names. Can you see that? Maybe you can see on the screen what I've done. So in the first row, first column, like A11 cell, if you click right, like normally the way we paste, it will ask you paste with the variable names. You paste with the variable names because then you don't have to type the name. You get my point? Like if you have 10 variables, you have to type the names 10 times, but it's a good idea that you actually paste with the variable names. Well, I do this way with the variable names. And look, all the variables, the names are typed. They're pasted. So I don't have to type them separately. You can, with this, like normally you do in Excel, you can increase or decrease the size, the width of the text, the column. You can change the column width. You can change the row width as well, like we do in case of Excel. Okay. Any questions, any issues so far?
When you copied the originals, did you include the names, the variable?
Yeah, only then they will show up. If you copy the name from Excel and then paste it in the first row, first column, only then you can paste it. Otherwise, SPSS will not know what you want to write down. It's very important that we all go together. So I don't want to leave anyone behind. You mean from the how? Yeah, I can do it again. No worries. I can do it again. I can take the blank spreadsheet, or I can clear all my cells. Sorry. So if I clear the data, it goes away, all blank. And then this was my original spreadsheet, right? Okay, so what I do now, I'm going to select, it's easy to select all and till the last variable, right? Is okay? So see, you can see that these letters M and OP is also highlighted. And then I use normal copying function. And now it's live, so you can see the activities going on. And then I go to my SPSS workspace. I see the blank sheet and I click here, the first row, first column. Are we all together? And then when you normally, if you click right, you will see paste with variable names. And you click that. And then you see that these names and everything and data is there. And because if you can't read it properly, then you can increase the width of the variables so that you can see them clearly. Eh? Are we all together? Good, good, good.
Does it matter that when I copy the columns, the first four have a ruler as an icon, and the rest of them have
some other signs?
Yeah, like blue, red, and A.
Yeah, I'll come to it. I'll come to it. Do you see that? That now the data is available. But be careful, one thing. There are certain things which SPSS doesn't like. If in your Excel, oh, sorry. You can see that when you, in fact, this will not be a problem when you're copying and pasting the data from Excel. But sometime if you have to write the name by yourself in SPSS, SPSS doesn't like space between the two letters. So they should be together. SPSS, when you name them, doesn't like certain signs or symbols. So try to make sure that you don't take them. If there's an error, let's say I'm copying and pasting the data and some error comes, then the problem 99% cases is not with SPSS, but the problem could be that the way I write the names of those variables in spreadsheet, or something is wrong with my spreadsheet. Even it could be about data. Maybe in my data, I'm writing comma. At some stage, I start writing decimals, the dot, or maybe in some data, somewhere in the data, I have by accident put some $sign or something, which SPSS dislike. So make sure that before you go there, it's a good idea that you have a quick view of your spreadsheet. And if you notice something unusual, make a correction there rather than in SPSS. Now, the problem is that there's one challenge which comes to originally immediately into my mind, is that we have the data in more decimal places here, right? But when I type it, when I paste it in SPSS, it only shows me 2 decimal point. Yeah. Sometimes it doesn't matter, but sometimes it matters a lot. It matters a lot sometimes. Imagine that your data must have, imagine your data is the whole column is 0.0039, 0.0085, 0.00. So the first number comes at the 3rd decimal point. And if you are not aware of this thing, which you said about decimals, it could be that your whole data in SPSS is 0.00, 0.00, 0.00. Why? Because it's not picking up the 3rd decimal place. So it's very important that you are able to ensure that your data as it shows in Excel is also showing in SPSS. If not, then make some adjustments with the decimal points, right? And how you do it? Look, you have a data view. Can you see here in the left, in the bottom left corner, there's a data view. There's one more view called variable view. Yeah. If you click variable view, it will show some characteristics of the variable. Normally, you don't have to do much to make any correction. But the first thing you need to make a correction is that make sure that do you have the enough decimals. By default, SPSS would be having 2 decimal points. But as I said, that sometimes your data is 0. All the the data is 4 decimal points, and the first 2 decimal points is 00. And if you don't make a change, the whole cell will become 0 basically. So it makes, so you lost a variable basically.
Then the SPSS and do it right after that.
Sorry? Yeah, that's what I'm going to do. You will see now. Look, the default setting is 2 decimal, right? And now I make, let's say 5 decimals, 2, 3, 4, 5, and check. This has, the data is back. So data is there. SPSS has absorbed the data as such from Excel, but the problem is that it's not showing up. Why it's not showing up? Because the default setting is 2 decimal points. So now that's not a big deal. You can change your, look, it again depends on situation. If your whole data is in 2 digits, you don't need to change. But I personally always advise my students that at least have certain minimum decimal points. I mean, more the merrier. It will not make any problem for you. But if you don't have them, or if you have less, it will be a problem. So usually you can have 4 to 5, 6 decimal points. You can't have endless decimal points. I think after 7, it says the error. If you have a data which contains more than 7 decimal points, and it's important to show then make some correction in your data, convert it to percentage then, so that it shows bigger values. Daniil?
That also makes some problematic things with the analysis of the data. You do like more decimal places, takes more and more time. Like to analyze.
It does. It's not easy. But then at the moment, our job is that our data should qualify to be analyzed. We will have we'll have the problems, of course, but yes, yeah.
Only like present some data.
No, we will do the analysis. The purpose of SPSS is to analyze the data.
Does it sort of like matter? Do you need to like change the default settings for decimals?
You can change the default settings. You can, honestly, I don't know. I never do it.
Well, then when you do that thing, what you want to do, analyze the data, and you get the end result. So does it, is there any sort of like consequences on the end result?
Yep.
Whether you change the decimals or not?
It is. It definitely is.
It is.
Definitely.
So yeah. So it's affecting on the results.
Yeah. It's important that you change the data. Like, for example, in the financial markets data, the stock price may increase by maybe the third or the fourth decimal point of a euro in a day. And you are not adjusting your decimal points, then all the change, all the phenomenon is lost. And as I said, that if you have a variable which is important to be displayed with the 4 decimal points, but you don't change the decimal settings here, then you basically have lost a variable. And that variable could have been very important variable in the study because it's all zeros. So it's very important that you make changes in the adjustments. Yeah, it does affect quite significantly. Usually we expect that the data would be numeric, but sometimes the data could be string, variable, some other signs. String variable is that when you have some strange, weird signs, like sometimes the data contains some symbols, right? Well, so that string variable could cause the problem. It's very important that your data, try your best. You can't do in every case. You can't do in every case, but it's always desirable that our data is in the numeric form, which means it's in the number form. If I write $250, it may sound a numeric, a logical number. It's a logical figure, but it's not purely numeric figure. The numeric part is only this much. 250. Dollar is not a numeral. It's a string. Okay. I'm not saying that it's impossible to work if the variables are in some other form, but it's much easier. The life becomes much easier if the data is in the numeric form. Okay, so this is why the question was that in this case, when the data is the numeric form, look, this type of brick is there all the way. This symbol, okay? But if it's a string or something, then it may have a different sign. Let's say if I want to say that the working population I want to have in the string form. Let's see. Yeah, then you can see that there's a different kind of 3 balloons here. So these symbols change according to the change of your data. But as I said before, it's a safer option to have the data in the numeric form, because numeric means straightforward calculation. There's nothing to worry. But there can be, if the data is in the string variable, there can be a problem, because if, for example, one figure is $250 and the second figure is 370, but with the pound sign, and the third figure is 290 with some asterisk sign, then you want to add them up. You can't do it. You see, because the unit of comparison is not same. So therefore, it's very important that try your best that don't bring any unnecessary symbols and signs into this. So I bring it back to numeric. And again, it says 0 decimal. No. I need 4 to 5 decimal points. So this is how. So you can see that you have the variable view, and you don't need to do much here. We have the scale. Not the, because I changed the variable's shape. So that's why the sign changed. Try that you are having numeric and scale variable, which is the best. But I will not pay much attention as long as my variables, this part is numeric and the width is 7 to 8. Of course, if you have the billions of digits, you have to change the width. I'm not sure if you can. Yeah, you can change the width. But the default setting, our data in this analysis, the width is 8, which means 8 digits, basically, So we can, including the numbers before decimal and after decimal. So the width is 8, we can live with it. But if the need be, you can increase it. Normally, we never decrease it because it's fine. It doesn't harm. Okay, so this is how the data looks like. Ideally, we prefer numeric, and measure is scale. But as I said, it will not be the crime against humanity if you ever get some funny symbols. It will not make much difference, to be honest. Yeah, but this is what we desire.
In our data, I can see some data that have 5 digits and or even 9 digits. So I don't understand the name update. Which
no, our data is less than. Yeah, we can. You have 9 digits. So it means that's if you. Yeah, that's a good point. It means that some last digit 0.000 somewhere we have missed out in some case. Right? In the data view, right?
Yeah.
Which one? Population density. Okay, so 1, 2, 3, 4, 5, 6, 7. I think there's some additional zeros there. But the width is definitely more than 8. Yeah, that's a good point. To be honest, as a practitioner, I don't care about it. Normally you don't have very massively big numbers. I don't think we have those trillions and zillions, I think. If the need be, we can have some, like for example, when we do the financial analysis, it's a very good point you asked. We have the data of sales, revenue, profit in $1 million already. So, the 6 zeros are already taken away. So instead of writing, let's say the revenue of British Petroleum last year, let's say hypothetically, is let's say $3,765 million, right? So I would say when I write my Excel, I would write revenue bracket in $1 million, and I would only show 3765. So I will not show 3765 and then 6 more zeros. There's no point of that. It doesn't harm anything, because so this is why how you take the data in Excel, right? So that saves. That is why good that you noted. I will not even notice it, the width, just whatever it is. But I'll be very careful about decimal, because if the variables are very small values, and decimal points, it's a problem. Not having, yeah. Okay. So we come back to data view. Is it okay? We come back. And actually, you can save this file in your computers. I don't know which is the right place that you can, you have your cloud thing, yeah? So you can save it, whichever computer you open. Am I right? Just a sec. In statistics, we don't start the very highly sophisticated analysis from the word go. Like you have a movie teaser, or like you have some book review before you read the book. Sorry. We also have something called descriptive statistics. It basically shows the key characteristics, some of the characteristics of the data. You can't draw major decisions or major conclusions based on this analysis, but it's more like how the data in its form, in its nature look like. So I would say that the descriptive statistics is the first version of the data analysis in SPSS, in statistical analysis. Of course, SPSS is only a system, is only a platform where you can use it. But descriptive statistics, the word is description, describe. It doesn't analyze too much. It doesn't do very deep down analysis, but it only describes the key characteristics of the data, okay? And we have several forms of descriptive analysis. The most common one is the mean, median, mode. Have you heard these words before? Mean, median, and mode. The mean is the average, even though mean, median, mode, they all are averages, basically. But generally, whenever the word average comes, we basically refer to mean. Mean means, if I say that there are 3 students in the class, one got 40 marks, other got 30, the third one got 20. What is the average or the mean marks? Mean and average are so synonyms. And what you will do, you will simply add 40 plus 30 plus 20, and you divide by 3, 30. So you will say that our mean marks are 30. So you are considering the value of the data, the numbers. That is called mean. If you want, I can give you actually an example. I can create a new file here. Let's say marks. There are 5 students. Let's say student 1, 2, 3. Sorry. Let's say we have 10 students and their marks are randomly given. Well, it doesn't mean that the first student have got the highest marks. So it's 30 marks, 27, 15, 28, 45, 33, 40, 50. Why I'm using Excel? Because I want to introduce the concept in Excel, but then the calculation we will do, the real calculation we will do in SPSS. And you want to find the mean marks, okay? So we have the mean marks. As I said before, that conceptually, mean is an average. Median is also an average, and mode is also an average. But in the normal language, mean, average, always, the first image when it comes to average, we think about mean, right? So what we do here, you have the average. Look, even the people who design the software, Microsoft, they have used the word average. So if you keep searching by mean, you will not find it. You will only find it by average. So we have the average and we select the data. Average marks in the classroom are 32.7. Does it make sense? Now, if you see, when I calculate the average, I consider 2 things. I take into account the number of data set I have got 10 observations, 10 students, and I also take into account the values of marks, 30 marks, 37 marks, 42. These two things I need to keep in mind. Then comes median. Median is a very special type of average. This is an average which keeps into account the position, not the value of the data, but the position of the data. So the median value would be, median marks would be, if I say, hey, there are 10 students sitting in the classroom, they got different marks. What is the marks of the student who come exactly in between the low mark student and the higher mark students? So basically, I'm finding out who is exactly sitting in the middle of the class. The others have either more marks, 50% of the people have more marks than him, or I can say 50% people are having less marks than him. So basically, if I have to plot, if these are marks, then half of the class is having marks higher than him, or I can say that half of the class is having marks less than him or equal to him. You see, when I say half of the class more than him and half of class less than him, you have to be a little bit careful that I'm now talking about more than 100% population, right? So what I'm saying is who exactly come in the middle of the data, like a cutoff point. If I say, what is the cutoff point of marks? If I have to judge that what is the cutoff point of people who are having more marks and less marks, then I would be considering the median marks.
So if median is an exact numeric value, not a scale of median, what's the difference between?
I'm showing it. Let me do it, then it'll be clear, right? So what we do here, we have the median. Yeah. Median is the number which divide the data exactly into 50-50. And this point become a cutoff point in between. And one more thing, which I would repeat later on, and I would show with the example in a few seconds, that in calculating mean, you take the original value of the data. But to calculate the median, we don't take the original values, but we take the position of the data. It sounds a little bit complicated, but when I show it to you, it will be very straightforward. So the median, the data selected, the median marks are 31.5. The question is, what is 31.5? Okay, let's do this way, and you will help me now. Let's start arranging this data of marks in some order. And the order is either ascending, in other words, from smaller values, from the smallest value first, and the highest come later. Or the order could be descending, which means the highest comes first and the lowest come at the end. I personally, I don't know why I'm comfortable with writing in the ascending order like anybody else. I think most of us would try to write the data in the ascending order. So what we have done now, please tell me, what are the least marks here? Least 16. Look, in the classroom, there was a student with the roll number 4. And when we calculate the mean, we don't care. Big number can come first, small can come later, and so on. And we are not considering the order, okay? But when you calculate the median, the order is very important. Here, when I calculated, I didn't care about the order because the software does it by itself, okay? But if you have to do it more manual way to prove the theory, then we have to write it in the order, either ascending or descending. So who comes after 16? 24. Make sure that the number is not repeated. If it's a repetition, then do it. Then 27, 28. Look, now I'm arranging the number in the ascending order. 30, only once. 33, 34, then 40, 45, 50, 50 is 50. Position. How many students we have now? 10. If you want to find somebody who's exactly sitting in the center and the number of observations, if the number of observations are odd number, right? 9, imagine. Then there's a 1, 2, 3, 4, 6, 7, 8, 9, and 5 is the only person sitting in the middle row. It's easy. But the problem here is that we have even numbers, and the numbers are 10. So we have 1, 2, 3, 4, 4 up, 4 down. And in the middle, not one person is sitting, but 2 people are sitting. What to do then? Then we just find the average, like we do in case of mean, because we have 2 people, right? So what is the average of 30 and 33? Does the software find 31.5 for us? For the median. Now, please tell me one thing. If the first number is not 16, but 6, and the last number is not 50, but 500, will it change the median?
No.
Because it's a positional value, it doesn't take into account the exact numeric value. It's all based on position. This is, and the first number could be anything. The only time the change in the value would reflect if the number or numbers in the middle, if they change. Like if 30 or 33, either one of them change or 2 of them change, then it will affect. But otherwise, look, before 30, it's 28. If it is 27, well, of course, yeah, that's a different thing. If it is 29, will it change? Will anything change? Or if the number after 33 is not 34, but 39, will it change anything? Guess what happens now? We are not considering the value, but we are considering the position. We're not considering the numeric value, we are considering their positional value. This is the beauty of median, because sometimes your data is having extreme numbers. Some of the numbers are following a pattern, good number, they of course they're different, but within a limit, right? But suddenly some big value comes and that spoils the show. In that case, to have the least effect of the extreme numbers, we sometimes prefer median than mean.
And if you would have 11 students, we would calculate the average of 1.
Yeah, let's say we have 11 students and it's 60. Let's say the 11 student. Now we have 5 up, 1, 2, 3, 4, 5 up, 5 down. 33 is the median. And if we do here also, let's say 11 students, and we have 60. And now the median would change. We need to keep the E14 cell also into, so the number, it changes. I still want to prove my point with a real example that the extreme numbers can be very dangerous. The extreme, let's say there are 2 numbers, and they're not marks. Let's say in this case, we talk about the money in the pocket money. You know, let's say this data is about how much money you have in your wallets. There are 2 students who are super rich, or they got some lotto, and what happens? One of them is having 5,000, and the other is having 6,000. Look, the mean value changed, but the median is still 33. And guess what? In this data of 11 people, tell me who is representing the data. Is this number or this number? For most of the data, who is the most, which, whether mean or median, which of these two statistics is a real representative of the data? Median. Because it is so immune to be affected by the extreme numbers. And guess what? When your average is 527.7, it's not close to any of this number. 30 is too small, and 5,000, 6,000 is too big. There's no other number in the data which is having 3 digits. Can you see that? There's no 3-digit number in the original data. But our average is in 3 digits. So who does it represent basically? So the traditional average can be deceptive because it can be influenced by 1 or 2 extreme numbers, and then everything is lost. I would say that if this is 50, okay, let's say that the whole data is well behaved except one person, and this time we can keep him 6,000. The mean. So if I this represents nobody, but median is something like some yogi, some guru, meditation, who is not affected by not affected by happiness, not affected by sorrow. There can be rain, there can be thunders, there can be snow, but calm, in full nirvana. So median is a more peaceful, is more like a meditational statistical tool than the mean. You see my point? But I tell you something. Despite the fact that I have been castigating mean a lot, we use it more often than not. You see, this is the most often used average. The mean. Median we use, but with some caution. But median is a little bit more refined than the, yeah. Another thing which is also an average is called mode. The mode is the number which is the average which we use the least, I would say. But the definition of the mode is that number which comes more frequently, which appears more frequently, is called mode number. And the number which appears more frequently is called mode. The number which doesn't appear more frequently, we will not go into it because, as I said before, we don't really calculate it too much because it's a very vague concept. Most often we use mean and median, and out of mean and median, we use mean more than the median. Now, I can, you can ask me that, Shab, if it is so easy to do in Excel, why do we have in, why do we do it in SPSS? As I said, there are two answers for this. The first answer is that these mean median stuff is a very basic analysis. They are not really real cause and effect analysis. This is just like a movie teaser, or you just want to see that how my data looks like when I start analyzing. You have the spreadsheet, you spend a lot of time in preparing the data, collecting the data, and now you want to see that, hey, what are the key characteristics of my data? You can't hold your excitement. That is the only reason why we do the descriptive statistics, mean or median. Okay, so it's like a first very basic analysis. Then the real, I won't even call it a real deep down analysis. It's a very surface level analysis. Now we come back to our SPSS. Look, 90% times, or even more than 90% time in the SPSS workspace, you will be using this function called analysis. This is the real magic wand with you. This is the real thing with you, which you'll be using. So you can click analysis. You have a question? Okay. So in the analysis, go to descriptive statistics. I'm going step by step so that we don't lose track. So I repeat, first we go to analysis. In the analysis, we have descriptive statistics, and then look at the arrow on the right side. There is something called frequencies. So I take a pause here. Analyze descriptive statistics and frequencies, right? We all here, click this frequencies, and this window would pop up. This window, you see it? I can use the metaphor of football. In football, you know that there's a dugout. Dugout is a place where the players are sitting. The manager, the coach have not chosen the team yet. And then the captain, after consulting the manager or the coach, goes to the dugout and says, hey, you guys, you are in the playing 11, you are in the playing 11. Sorry, mate, I think you need some rest. You were on there last time. Yeah, you see my point? So this is a dugout, and this is the football pitch. You see here the variables. So we want to choose which variable we want to make them play. Okay. In this case, it's very easy for me that I can select one of them, or I can send it back. And by pressing the shift function, I can choose the variables if I want to take all of them. You see my point? I can choose the variable one by one, or I can choose the few and I can choose not to choose a few. Or by pressing the shift button and with the arrow down, I can select all. In this case, I think I want to select all. You know, I want to see how my variables look like with at the basic level. And you can see there's an arrow here. Yeah. Can you see? Which means that take the players from dugout to the pitch, and I took them in the one go. If I want to deselect them or deselect one, then I can choose, for example, let's say that I don't want to talk about alcohol consumption right now, because maybe this variable is not complete. Then I can take it back. I can just take it away. But let's assume that I want to study it. So we bring it back. Are you here? So let's make a rule that if you are not keeping pace, only then you tell me, so that I can repeat it. All right. Statistics is a function. Statistics is a function here, right? Do you find something familiar here? Yeah, exactly. So you have the mean. So these are all descriptive statistics. So this is a set of all the descriptive statistics that one can have. And these are the most common descriptive statistics that we use. As I said, we can choose mean, we can have median, okay? If you want to take mode, you can, but I must use a word of caution that mode is the average that we don't use very often, because sometimes it's not very conclusive. But mean, median, of course, they're most often used. I'll explain these things to you. What is quartile? What is this? What is that? But at the time being, please ignore them, okay? We take this one, standard deviation. We take variance. And don't think that I have forgotten to explain them. But I want to do opposite. I want to first play with the numbers, show something, serve you in the plate, and then discuss their conceptual value, right? Then we also take maximum, minimum, and range. And I will also take skewness and kurtosis. So as if that was not enough to make you confused, and I added more. Skewness and kurtosis. Sorry? Standard error. Yeah, but we don't do it we do it, but we don't do it very often. So it's like we basically cherry pick, and we are doing cherry picking of those descriptive statistics which we use quite often. So I'm not taking those very rare ones to be used, so though I will explain them, but I haven't forgotten. So you can click what you want and what you don't want. All right, all good. And then you continue. Yeah, you continue. So it means that you have chosen your statistics. Another thing you can choose are the charts. You also want to show that how your data look like. If you display, look, so far we have only been talking about the numeric calculations and the numbers. Will you not like to see that how your data, when you plot it on a graph, how does it look like? You should be willing to see it. The most common one I use is the histogram. And you click show with the normal curve on histogram. I'll show you why I ask you to choose this function. Histograms and show normal curve. And then you continue. These are the only two functions that we will be using here. We will not be using any of the other functions. Statistics are chosen. Charts are chosen. This may not be required. Okay. Charts are chosen. Yeah. Continue. Sorry. Statistics are chosen. Yeah, it's fine. We have chosen it. And then we click. Now, after making a choice, you have to click OK. Right? Click OK. And guess what? Another window of SPSS shows. Huh? It will show. Just wait. It takes time because the graph, it takes time to show up. Yeah. So you have you have the mean, you have the median, you have the standard deviation, everything basically of all the variables which you decided to take. Yes.
There was also like one option, choose create APA style table. Are those like tables any different from these?
No, we don't choose them. No, there's no need.
But now that you get the results and for example, the chart called alcohol consumption. That is,
yeah.
So is there like a certain way that you can add also the like values, for example, like the liters or
the values of what?
Like is it like 3 liters or
3 liters?
Yeah, so because now it's only like presenting that when you select the alcohol consumption, and then it's only like giving the value.
Look, it depends upon the way you define the variable in your spreadsheet. If you have chosen alcohol consumption, I don't know. Look, the variable alcohol consumption can be interpreted in many ways. Maybe you took in the real consumption, how many liters in a city, or you have taken alcohol consumption of per capita alcohol consumption in the city. The total consumption divided by the total population. So it depends how you defined. Now, when you say total consumption, per capita consumption, or you are also seeing what percentage of population is consuming alcohol. Look, in this case, the liters will not appear up. If I want to find out what is the percentage number of people drinking alcohol in Uvascula, you will not say in liters, you will say in percentage. Yeah. Yeah. So let's say for the sake of argument, let's say that I measure this variable alcohol consumption with the where is this variable? With this, let's say I calculated this alcohol consumption variable as an actual consumption per capita consumption in the city. So for example, if the mean value is 1.98, I can say that there is a 1.98 liters or gallons or whatever barrels, I don't know how alcoholic people are in the city, per year in the city. So I can say that, you know, out of all the cities, out of all the 500 something cities, the average consumption by one person is about 1.98. I think liters is too less in a year to consume. Let's call it gallons. Not barrel, gallons. So we can say that the average consumption in the all 500 something cities, in which we, you know, the normal mean that we add all the consumption divided by the number of people, the average consumption is 1.98. And if we arrange people with the low consumption and the high consumption in the ascending order or in the descending order, then this average is 1.94. So the guy who consumed 1.94 gallons of alcohol a year is standing exactly in the middle of the order when you arrange them in the rising order or the falling order. You see my point? So this way you can get some of these descriptive statistics, but I haven't finished them yet. Remember, I said nothing about standard deviation. I said nothing about skewness. I said nothing about kurtosis, right? That I will tell you after a break. Drink coffee, drink water, and come back. Okay, so we continue with those descriptive statistics. Before we went to the break, we discussed one category of descriptive statistics called averages, which was mean, median, and sometimes we use mode, very rarely. Another subset of descriptive statistics is called measures of dispersion. Dispersion means that how scattered the data is. The scatteredness, you understand the meaning of the word scatter? Scatteredness or the variability is a characteristic that how much data is well integrated and how much it is spreaded around the average. Well, what I'm saying now may sound a rocket science, but let's continue with the same example, first in Excel, and then I would show you with SPSS. Imagine we have the same question of marks, and we want to find out what is the extent of variation of the data. Try to understand. It's very important that you understand a little bit of theory behind dispersion. Is that imagine we are studying a relationship or we are getting a data that the crime rate. And we are measuring crime rate here on the y-axis, and here we have those observations. Let's say those 500 cities that we were talking about before. Observations, whatever it is here. Yeah. It happens that we expect in theory that crime rate. We plot the crime rate data of different cities. Some values are here, some values are here, some city is here, some is here. So if we draw a line, straight line, this hypothetical straight line, we find that all the real points are not far away from the middle line. If we have this hypothetical line and we assume that everything is around the average, basically, you know, there might be something, some cities, let's say that this city is very peaceful. Let's say this is Reykjavik, which is very peaceful, and then this city is somewhere, you know, I don't want to name the crime rate. So there's couple of outliers. We call them as outliers because they don't go with the mainstream pattern of data. You see my point? We use the phrase outliers for those observations which can be very far away from the set pattern of data. But there could be one or two outliers, but what if we plot the data and the pattern comes like this? So if you draw this hypothetical line, you find that in the previous example, the range of variability of data on both sides of this fictitious straight line was very narrow. You see my point? But in this case, the range of variability of data is rising. It means the data is not condensed. The data is not very well gelled with one another. Data is spreading. And this spreadness or variability is also an element of riskiness. Variability. It's like you meet somebody. This person in certain situation can be very happy, very jovial, but on certain occasions, he can be extremely angry. Is this person risky? If I want to use the word riskiness, is the degree of riskiness higher? Because he's so unpredictable. Same thing can happen with the data. This variability, this lack of predictability of the data can make certain data sets highly risky. Highly risky means they are difficult to analyze, and the results that we derive from them may not be so valid. Because we just chose certain random numbers and they go along very well, but otherwise there can be some problem with the data. There's a lack of, okay, one more word, maybe you will like it, consistency. The consistency is lacking in the data. And that is the measure when we are calculating the measures of dispersion. My finance friends will agree with me. We do a lot of research on stock prices going up and down, but we also calculate which stock is risky investment. I mean, it can go up in the one go. Yeah, look, even if you compare this way, the stock price can go really up, but then the next moment it can fall a lot. So the investor who invests in these stocks is taking a massive amount of risk, right? So not all the investors are risk lovers, but some go for risk lover because they know that if it all goes well, they would be millionaire overnight. And they're also prepared to lose millions if things go unfavorable. But we also have another set of investors who want to take very measured and very meager and very calculated risk. You see my point? So for some, this measure of riskiness is very important, not only in our personal life, like as I said, that it's easy to get along with somebody who is more consistent behavior rather than somebody who can be very temperamental and, you know, the mood swings and stuff. So other way around, this can be this. So the variability in real life is showing basically the lack of predictability, because you can't estimate, you can't guess the next move of the person, or you can't guess the next move of the market. Like cryptocurrencies, it can go even lower, almost zero, or it can skyrocket. And that can totally confuse everybody. So therefore, the measures of dispersion we calculate to make the predictability, consistency thing understandable. I want to give you one example in Excel, and then we will go in SPSS. All right. This is my favorite example. Daniil must have listened to it many times. Daniil, have you? Okay, let me make it. It's about the football pitch. You know the football pitch?
Yeah, I like it.
I love it. I'm sure you love it. I want to give the football metaphoric example. So we have Manchester United. We have which other team we should take? AC Milan? Is it even a team? It's not a good team. You think so?
They won the Italian championship.
Italian championship. Come on. Our Vascula can win Italian championship. So there's AC Milan. There is okay. I take Manchester City, and then we take, let's say, Celtic. Everybody hates it. Celtic. Each of this team played 5 matches. So match 1, 2, 3, 4, 5. Manchester United scored 4 goals in 5 matches. AC Milan scored 2, 3, 4, 6, and 5. Manchester City scored Celtic scored 8, 2, 0, 3, 7. If you look at the sum of goals they scored, let's call sum. And then we can expand it to the other. They all have scored 20 goals, right? So obviously, if each of them played 5 matches and each team scored 20 goals, so we don't even need to calculate the average goal. The score is 4, basically. So each team is scoring 4 goals. But let's calculate let's call it sum. Let's call it mean. And how we calculate mean, we add average here, and we select. And if we have 1, then we can extend to the other. So each team is scoring 4 goals. So it looks that each team is equally successful so far in the league after playing 5 matches. Now, the thing is that the league is going on. In the first 5 matches, each of this team have scored 4 goals. So it looks that in terms of performance, there is no difference. Now, I want to make a forecast that, okay, what if each of them play 1 more match? Which of them is easiest to forecast? Why so?
5 matches played. In every match, they made 4 goals.
So we,
guess
even the next match, the highly likely, we don't say that they will score. We'll say it's a highly likely. So there is a prediction power, right? Which team or which teams are least predictable in this data? If you have to name 1 or 2 teams, who would you name? We don't know what they do next match, in the next match. And Celtic, because they can score 10 goals on a given day, but then they can lose they don't score any goal against the opponent. So it's difficult to foresee. This exactly is called standard deviation, dispersion. Now we want to see which of them is risky, which team is risky to predict for the future. Because prediction, we do a lot of in the financial market, we have to make some forecast. And the forecasting becomes very complicated if the scatterness of the data is massive. Okay, the formula is very simple. We call it standard deviation. I'm writing only abbreviation. Standard deviation. Okay, and it's very simple. If you only type in standard deviation here because we are taking standard deviation, and you select the data. And you can see here that the standard deviation is changing. The one with the least, sorry, I think I did wrong. Sorry, my apologies. Standard deviation, it's here. Look, I'm intrigued at this 0. Because if I use this metaphor, which I gave you before, new share, this whiteboard one. This one. If a team is scoring in one match 4 goals, second match 4 goals, third match 4 goals, fourth match 4 goals, fifth match 4 goals, then if I have to join these points, it will be like this. It should be a straight line, right? I can't draw it for you, but all the points are on the straight line. There's no dispersion. This is the average goal, right? The 4 goals are average goals. And if I see the real data here, the real data is also 4, 4, 4, 4, 4. So they all are lying. So all the points, try to understand. Basically, all the points are falling on this straight line. And when I see the second team, which is AC Milan, 4 is the average, so this straight line remains same. But sometime in the first match, they score how much? How many? E1. How many they scored in the first match? They scored 2, 3, 4, 6, 5. I'll remember it now. So they score 2, which is below average, 3, then 4, and then 6, 5, 6. Okay, 5 and 6. But if you see the pattern, the deviation is still in a very narrow range. Can I say so? And then you look at the third team. What is that data? It's it's 204410. 204410. Okay, so it's 2, 4, 0, 0, and oh my gosh, 10. So it's like a 2, 4, 0. This. Look at this is how the data look like. And even worse, if you look at the fourth team, it is 82037. 82037. Okay, it's 8, 2, 0, 3, 7. So this looks completely bizarre type of data. So this standard deviation, even though the performance per match is equal, but we are finding the problem to find the predictability, consistency of the data. Or in other words, higher the predictability, lesser is the risk of prediction. And sorry, higher is the standard deviation, lower is the predictive power of the statistics. And lower is the standard deviation, higher is the predictive power of the statistic. So this means, even though quantitatively is 4 for all the teams. But qualitatively, this 4 is not same. The quality of this 4 is the highest here. And the quality of this 4 is the least here in case of Manchester City, because the variability is very high. The predictive power is the least for Manchester City, and the predictive power is highest in case of Manchester United. So the quality of data is the most superior in case of Manchester United. You with me? Good. Now, when you did the SPSS thing, we clicked something and we click at standard deviation. And when you see the standard deviation of all the different variables, you can see that the highest so far with the naked eye is 106. Oh my gosh. And that is the population density. So it means that the predictive power of this variable based on the variability in the data is the least. On the other hand, we have one more variable, which is dropout density. Dropout density. And you can see that here the standard deviation is very less. I mean, 0.01, basically.
Please share this SPSS file after the lecture if it's possible.
Yeah, sure. Yeah.
Thank you.
You want? Okay, but even so that we all are doing it actually. Okay, all right. Okay, right. No problem. So you can see that the standard deviation is one. It's not a conclusive proof of the data. Okay, that is proved with when we do cause and effect type of analysis. But at least you are able to see with the naked eye that what are the key characteristics of your data before you analyze them further for more rigorous analysis, right? So it's like a bird eye view. It's like you are just taking kind of stock of your data, how it looks like. All good? We have one more statistics which we click and we can see it. It's called variance, which is just below standard deviation. Variance is actually the square of standard deviation. So we just square it. So 17 something multiplied by 17 something itself is 290. And here 45 something is multiplied with the 45 something and we get 2088. This is 0 because this number is so small that if you multiply, there's so many digits, it's nearly zeros, because decimal number, when you square it, it becomes even smaller. That's why. So standard deviation basically is a square root of variance, or the variance is a square of standard deviation. The question is, why do we have one? Why can't we have one of them then? Well, first of all, the standard deviation is a base measure. Variance is based on it. First, we calculate standard deviation, right? The second thing is that standard deviation is inclusive of sign. It can be plus, it can be minus. Can it be? Yeah. So the standard deviation basically show us the positive side and the negative side. I want to give you an example. Let's say, even though these numbers are not in the right order, basically this 0 means that on a given day, AC Milan can score average plus standard deviation or average minus standard deviation. And whether you plus standard deviation or whether you minus standard deviation, it's same. It means the least variation or the most predictability is of AC Milan. On the other hand, look at this thing. And then look at this thing. Sorry, my apologies. You are betting on AC Milan and you make an estimate, you know what, in the next match, they can score 5.58 goals or 2.41 goals. If I round them off, you can say that, you know what, in the next match, they can score either 6 goals or 2 goals. Whereas in the next match, the optimist would say they would score 4 goals. Pessimist will also say they will score 4 goals. In the next match, the optimist will say AC Milan would score 6 goals. The pessimist say AC Milan would score 2 goals. Optimist will say AC Milan MC would score 8 goals. And optimists say, well, 0.2 is no goal. So we can say 0 goal basically, yeah. And here, the optimists will say that they will score 7 goals and the pessimist would say they will score 0 goal. Can you see the prediction? So this X average is free from square, standard deviation is free from square, right? Then adding them is logical. One number is squared and the other number is not squared, you add them up, it's a little bit conceptual fallacy, right? This is why we have the standard deviation. The variance we take because it removed the linearity of the data, that's why, but I will not go too much into it. But I would say that mostly the researchers, the first time user, they like to use standard deviation more than the variance. Otherwise, there's no real difference. Variance is just the square of standard deviation. Make sense? And actually, if you want to find out, okay, we call it SD, mean plus SD. And this is mean minus SD. Daniel, if you remind me, I would also share this spreadsheet with students so that they can first see in Excel and then in SPSS. Yeah, you can also find out the variance. And again, the formula is very simple. You just need to find something called var, which is here, variance. And you need to select the data. Square, 0 square is 0. So, and you can see that this is a square of this. And okay, I can choose them for some decimal points. Maybe they have many decimal points, so I can also have the same one. So number and maybe 4 or 5 decimal points, 3, 4, 5. Okay. So exact numbers you can find out. Yeah, it's nearly, yeah, this is something like that. Yeah.
Sorry, I kind of lost myself at some point. I actually thought that mean plus standard deviance and mean minus standard deviance are the variance, like the uppest and lowest.
No. Variance is different. So basically we are saying, let me show you in another conceptual way. Just a sec. So basically we're saying that if we have a data set and we have a normal distribution curve, very symmetric, bell-shaped, then this is the average. We call it X bar as average. Then we go 1 standard deviation on the right side and the 1 standard deviation on the left side. And this deviation area on both sides is exactly homogeneous. It means that basically try to understand standard deviation in a real life sense. Standard deviation is like a leeway you want to give that, okay, within this range, the data can move. But as you become more and more relaxed, then you have to make a compromise with the data. Then see what, if we have 2 standard deviation here and 2 standard deviation here, look at this area. You have to make larger compromises. Now you have to add this part also. So this is the idea, that how strict, how rigorous you are, to what extent you can take the likelihood of error in acceptance. You see, we all follow different rigor. When you are the boss, when you are running a department, and there is some accounting figure estimate of sales made by some of your, the finance manager, and they make some estimate for the next month's revenue, and then you are comparing the actual revenue next month and the estimated revenue for that month, but made previous month. And then you want to see that, hey, what is the difference between the estimate and the reality? And you say that, hey, Mr. Accountant, I will give you a pay hike if the gap between the estimate value and the real value is less than 5%. But if the gap between the estimate and the real revenue is more than 5%, don't expect any raise, or maybe I sack you if you do it. We make, because otherwise people can cook up with the numbers, any numbers basically. I know everything is not in accountants' hands. If the machinery breaks down, if the market goes down, if there's a political issues in the next door, that's not his fault. But then the employer should also be sensitive to the fact. But if given the normal time, all else being equal, ceteris paribus, we want that the forecast value should be as close to the real value, or the real value. Yeah. So that's why we use the concept of standard deviation. So intuitively, even though the company is not using the concept of standard deviation, maybe if you ask them what is standard deviation, they would give you a blank stare. But in reality, conceptually, they're using it, because we want that our estimate and the reality should be as close as possible. That shows the quality of your estimation. Otherwise, why do we make estimates? People, CFO, accountants, managers, CEO, they are giving presentation in the board of directors. They can say anything otherwise. So even without being aware of this concept per se, people use it. Haven't you seen before the elections, there are some exit surveys, polls that this party is likely to win, even before the elections are cast, the votes are cast. And then we see the actual election results, and then say, all right, bring the column where this news channel, they made the estimate for each candidate, for each party, and let's see how many votes they have got in reality. Which estimate you like? I'm sure where the gap between the estimate and the reality is low, then you start trusting that channel. And these people are nice guys. They really make good estimates. Their data, their estimates are objective. So the standard deviation also touch upon the objectivity of the findings, basically. So that's why this is very important concept. In finance, we use a lot, actually, almost every day. Yeah, Daniel, you can ask him. He's a victim of standard deviation. All right. And then we have another concept called range. Range is very simple to say. Range is a gap between the maximum and the minimum value, basically. It's a very easy thing to do, basically. We just see that what is the gap between the maximum value and the minimum value. And you can see here in your estimates, there is in the crime rate, the minimum crime rate is minus 3.1. It means there's one city actually where the crime rate has fallen over time, and that is minus. But there's also one city where the crime rate is 400. So it means there's one city among the 500 cities where the rate has changed to 500. So there's a 400% rise in the crime rate. And then the range is in between the two. Yeah, range is, look, I hope the cursor is visible. Range is the maximum minus minimum. But the problem is that if the minimum is negative, then maximum minus value become plus value. You see that? If you have minus times minus, it becomes plus. So here you can see, for example, the minimum is 8.8. The max is 8.8. The minimum is 8.7. And here the range is very narrow, very small. And so on and so forth. You can see that. But this is something only a kind of baseline. We just want to see. As I said, descriptive statistics are not something which you can base your decision on, but this is like a first-hand encounter with your data, that how it looks like. Of course, you can make some decisions, but not full decisions, just based on, if there's an accountant, he makes some estimate for the revenue, and the gap is quite high, then it needs further investigation, that why the standard deviation is so high, and then, but we don't make a decision exactly based on that one value, okay? So therefore, we need to be very careful. So we have discussed mean, median, standard deviation, standard errors, I don't know where it come from. Maybe by default, range, minimum, maximum. We're missing two things. One is skewness, and the other is kurtosis. Skewness and kurtosis. To see the skewness and kurtosis, I need to take you to the slides. Skewness. Skewness is measuring the symmetry of the data. In the normal distribution type of curves, as you can see in case of here, both tails. So if you plot the data, you will see that the data look like a bell. And this is the center. You go a millimeter on the right side and you go a millimeter on the left side, the height would be same. So if you have to make a bar here, it goes up. And exactly the same distance, you make a bar here, they would exactly match with each other. Yeah. This is a perfect symmetry of data, and here skewness is 0. Nothing. There's nothing, no skew. There's full symmetry of data. Any point on the right, any point on the left, they are fully symmetric. But the problem happens if you plot the data. It looks like this. Or you plot the data and it looks like this right-tailed. What does left tail look like? Just the mirror image. The data, when plotted, looks like this. Right-tailed. Why we call it right-tailed? Because in the center, the right side is heavier. You can see that most of the bulk of the values are on the right side. And here, if I draw a center line here, the average, the mean, the left tail is heavier because most of the data is lying on the left side. So this can be right-tailed or positive skewness. And this is called left-tailed or negative skewness. And it basically shows that your data is very unsymmetric. It's not a conclusive proof that we reject the variable because it's unsymmetric, but we can do something like it's like a health check of the data. And based on that, we can do something to improve when we do the analysis, or at least we are cautious. So positively skewed, here there's no skewness. And here is positive skewness. I mean, here is zero skewness. Here is positive skewness. And in this case, that is negative skewness. Yeah? Does it make sense? Tell me one thing. When we were doing the first time SPSS descriptive analysis, did you see the skewness somewhere? Do you notice that you have seen skewness somewhere before? I think you have. Okay, I show you. Does it look like? Okay, maybe not this picture. This one. The bulk of this is the ideal, this curve, right? But if you look at the data, you'll find that the data is flowing like this, basically. So it's more like a left-tailed. And this same way, if you plot this one, this is a typical example of right-tailed data. You see, except for very few large value, the bulk of the data is on the right side. So it's a right-tailed test. Right-tailed skewness. So technically, when you are doing this descriptive statistics, and this is why I went to the plots. Remember, I went to the charts and the plots, and I clicked this thing that, okay, let's see not only the numbers, but also see how the data look like when plotted. Ideally, and this is something similar. And here you can see the skewness, but I'll come to kurtosis later. This is skewness. This is skewness. So if you plot the data, it'll look like the right-tailed. If I plot this hypothetical data curve, it will look, the bulk of the tail would be on the right side. Like in health check, we have some measures, which measure is good, which is bad. Statisticians, they agree that your coefficient of skewness is, the data is fine if the skewness is between +1 to -1, or at least close to +1 and -1. So even though it's a +1.25, or if it is -1.25, it will not be a big problem, but it means we are living on the edge. Ideally, the skewness coefficient should be between +1 to -1. And if it is, then we can conclude, or at least we can make some educated statement or some guess that our data is pretty much symmetric. And now, when we see the SPSS findings, and you see the skewness here, yeah, this is under the range -1. This is under the range -1. Young age people data is under -1. The dropout density is under -1. Working population is also okay. Population density is also okay. Alcohol consumption is also okay. But when you see the number of cops, or when you see the education intensity, or the poverty ratio, or the worst one is crime rate itself data, you find that the data is extremely non-symmetric. Okay, but listen, This is just to warn you that here may be the potential problem when we go further. So you make some kind of notes or some circles, but that doesn't mean that we love something or we hate something, right? This is just to warn you that the current data has some inherent abilities or disabilities. But that doesn't mean that you totally make a decision based on these coefficients. So these are just the curtain raisers, like a teaser, basically, right? It's a first impression, but not the last impression of the data. Then we also have a concept called kurtosis. Kurtosis, skewness is about the symmetry of the data, and kurtosis is about whether the shape of the bell curve is too pointy or too flat. Look, when you see this shape, you find that it's like you go and you come down. But what if the data looks like this? Can you see the difference? It's too pointy. Or in other words, or another example, you plot the data. This pointiness, look, the symmetriness, when we check the symmetry, we look at right and left. Right side of the mean, left side of the mean. But when we look the kurtosis, we don't look right and left, we go top floor. And do we see that? Can we stand on the top floor? Is it like a small point that we can fall on either side? Or is it say that we can even play football on the on the terrace? Right? This is shown by this concept of kurtosis. Kurtosis shows the pointiness of the peak of the data. And once again, there are different statistics, they have different opinions. Some people say that even +3 to -3 is okay. But many people are saying that healthy data should be when kurtosis is between +2 and -2. But I have seen some studies where the researchers say that, all right, +3 or -3. Again, it depends upon the rigor. I would say that for skewness, most of the statisticians, they have unanimity, +1, -1. But here, there is a little bit of conflict, different opinions. Some people say that, well, it's a problem, but it's not a problem which can totally kill your analysis. So +3, -3 is okay. But some people say that no, you have to be a little bit disciplined. Let's put a limit +2 and -2, right? And let's see what we have. We have kurtosis. Oh my gosh, this first one is unacceptable. This one is unacceptable. 88, no. This is okay. Dropout density is okay. This is a kind of borderline thing. I would say young age people. This is fine. Working population is great. Sorry, this is fine. Working population is okay. Education is flat. This is unacceptable number of thing. Even though there, yeah, I think this. I'm noticing that the one who have bad skewness also have bad kurtosis. Yeah. So in this case, it's purely coincidental that those variables whose skewness is not good, their kurtosis is also not good, even though they are independent things. But I don't know, it's purely coincidental. It means that I have one more reason to be careful, that there are two common problems coming from the same set of variables. So then it gives me food for thought. Did I collect the data in the right way? Did I miss something? So that gives me some food for, I get a feedback about my data. All right. Or if I don't look backward, I can look forward And maybe in the future, when I do the analysis, I can change the form of the data a little bit. I can make them non-linear by squaring them or by cubing them or whatever, like log values I can take. Yeah. So I try my best that I don't want to tell you those things, what we can do yet. Okay. But at least we can either look backwards and see, did we commit any mistake while compiling the data, while writing in the Excel from those, because when you have research project, you might have several spreadsheets and then you combine the data from one spreadsheet, second one in the main master spreadsheet. You might have done some mistake.
Maybe you tools before the actual analysis.
Everything, basically. So all these statistics which we are discussing now, they are not undermining their importance, but we can't really make strategic decisions based on them. If this is not a research thing, but if it is a company's records, data, and we are having a board of directors meeting tomorrow, right? And the CEO has to prepare a presentation based on the data the company have and what is the future. A night before, if they do these descriptive analysis, they know that where they can be hammered, they can be questioned. Because in the board of directors, some statisticians are sitting. So it means they need to prepare some arguments already. So they can create some statements in their defense when they make a presentation tomorrow. You see my point? Yeah. So this is all about descriptive statistics, which we discussed. Okay. Of course, we have some more. We also have quartiles. Sorry, I forgot to tell the name. If it is too pointy data, that it's almost impossible to stand at the top, we call it leptokurtic, right? And if it is very flat, then we call it platokurtic. It's easy to remember the name, second name, platokurtic, because you see there is a mountain, there's a hill. We also have a landform called plateau. Have you heard the plateau? It's like a raised, but it's not like a pointy, it's like a flat. Yeah, like very Scottish Highlands, very plateau type, you know, the cows are grazing on the top, but yeah. So leptokurtic and platokurtic, you don't need to remember the name, but just an idea. Yeah. We also have two measures which I didn't discuss. We call them quartiles. The quartile is that let me cook up a story. You are studying the per capita income of a country, and you define that if people, whatever is the average salary of the bottom 25% of the population, we set it as a poverty line, that anyone below this 400 euros per month, let's say the bottom 25% people in the country, their average monthly salary is 400 euros. Right? So it means that you set a lower bar, that if somebody is below this income level, or you make an estimate that, you know what, in the current situation, the minimum wage or the minimum salary a month, which a household should get or a person should get is this much, because you make some estimate, food price, this price, that price. So I'm not talking about the food you eat in the expensive restaurant, but the very basic food, basic clothing, basic shelter. And you find out that, you know what, if a person in our society is earning or getting monthly income below 700 euros, we call him or her poor. And you can set the bar 25% bottom population. And then you want to find out, you know what is the middle class? You know, we often say that the middle class is the one which suffer the most. both in recession and also in the inflation. Then you can say that, okay, if 50% people salary is the exactly mean salary in the society, or the median salary if it is symmetric population, so it means that anyone above 25% population, and up to 75%, that is called middle class. And anyone who is above 75%, we call it upper class in the society. So let's see where the middle income people's range start and where does it finish. And remember, middle class is very confusing. We have upper middle class, we have the lower middle class as well. The one which close to the bottom 25% is lower middle class, maybe 26, 27%. And the one who are at the top, 73%, 74%, they can be called as an upper middle class. And then anyone above 75%, we say, okay, this is the, kind of the elite people, rich people. So this way we can make some segregation of society based on some socio-economic indicators. So in the World Bank studies, in the IMF studies, in the Asian Development Bank studies, they use very often the quartiles because that is where they define, Not only quartiles. Some people say that, what, we are also interested to know what the top 10% population earn. And then somebody says, we also want to see the poorest among poors. And we want to say, what is the living standards of the bottom 10%? Look, now I'm saying the top 10% and the bottom 10%. Then we change the word from quartile to decile. Does it sound sense? Like we say that it's like a deca is 10. I think it's a Latin expression. So then we use the phrase decile, top decile, bottom decile, because we are considering 10% of the population. Sometime you may be even interested in the same studies, how much is 1%, how much wealth is owned by 1% of the population. Now you're not clubbing 10%, you're taking one, look, in the 10%, we club more people. Look, the scale is getting more and more minute. First we have half this way, half that way, median, right? Then I say quarter, top quarter, the bottom quarter, quartile, top 10%, bottom 10%, decile. And then we're saying 1% up, 1% down. Then we call them percentile. Percentile. You see my point? Something similar study, why I'm saying it, that we don't do it for the sake of doing it. There is a reasoning behind it. Then sometimes we also see the studies that, what is the average salary of the graduates? And there have been real studies about it, and they find that people who are very intelligent, they get the highest marks, they didn't get the highest salary when they employed. Of course, the one who got the lowest, they didn't get the highest salary at all. But people who are in the range in between, so in the upper quarter, third quarter, they are the one. So they are not the best ones in the classroom performance, but they are somewhere between average and above average. They are the one. So if you are interested in this type of study, then you will definitely would be interested in calculating the third quartile. So basically, these type of things we do in various studies, and it's not necessary. I don't do it in my financial study because we don't need it much. But if I have some development economics type of study, as I said, something about per capita income, something about consumption of society, then I think it's a good idea to consider the quartiles as well. Yeah, but it's not easy. It's not difficult to calculate them. You can just use the same function here. We can call it first quartile, let's say quartile one, like the quartile one means the bottom from 0 to 25% of the population. So if you want to find out this, quartile, sorry, what did I do? Did I do something wrong? War. Okay. It's not a good example. Sorry, I'm just trying to. Few arguments. I think the data is not enough, I think, in this case. I don't know why, but it should be the case. All right. What is this then? No, I think for this, they need more data. Well, we can do here, no problem. We can go to SPSS and we can go to our data and we can do the descriptive analysis again. Remember that you need to use the analysis, descriptive, and frequencies. And here, actually, I can cut out all other things because I don't want to repeat it. We can take away all of them. We have done mean, everything, skewness, ketosis. Q1, maybe quartiles. So there are only 2 quartiles. So this one takes account of first quartile, and there's no second quartile because second quartile will be the median, basically, you know. So, and then we continue and click OK. Because the graph again came because it didn't take them away. But this is the quartiles, yeah. So you can see that. So this is the first quartile figure, and this is the third quartile figure. So it means that for example, the poverty ratio, what percentage of people are poor? The bottom level is the poverty ratio is 0.24, and the 75% is 4.23. So obviously, the third quarter value would be more than the first quarter value. So basically, we are when we calculate the quartiles, we are doing this way. That if it is first quarter, so if this is the population in a bar, then we see that how much is the first quarter, Q1 of population, the first quarter. And if we say Q3, then we say from 0 to 7. So this is 25% of the data, the bottom 25% of data, which is Q1. And if you want to study the 75% of the data, then this is called Q3, which includes 75% of the data. And if you find a difference between third quarter and the first quarter, this difference is very interesting. If you want to find the difference between the third quarter and the first quarter, that would show you the middle class. Those people, that data which falls in the middle of the population, right? If you want to find the absolute number of the middle income people or middle performer, then you just find the difference between Q3 and Q1. If you want to show it in the form of a percentage, relative number, no unit, but just a fraction or a percentage, then we divide this Q3 and Q1. Use the brackets, otherwise it can be wrong, with Q3 plus Q1. Then we can get the relative or the percentage, like I have shown you here as well, that you can calculate inter-quarter. If you want to find the middle income or the middle range, then you can find this in percentage terms. You can also do this thing. But if you're only interested in finding the absolute number, how many people are in the so-called middle income category in Uvascular? Okay, arrange them in the number, in the order, ascending or descending. Pick the bottom 25% and pick the bottom 75%, and just subtract the bottom quarter from the the bottom 25% from the bottom 75%. From, when I say bottom, means starting from bottom. Yeah, that would show the middle class living in Uvascular. But if you want to find what fraction of middle income people of total population are lying are in this slab, then you may use this formula. So divide by, then you will not be having the absolute number, but then you will be having the fraction or a percentage point. Yeah, make sense? So
So this is the formula, Q3 minus Q1. This is the fraction of middle class over the whole society. Yeah?
no, if you want to find, for example, if you want to find the, just for sake of middle income or middle performers or whatever, if you want to find the exact number of people who in this limit, so-called middle income people, then you can just find the difference between Q3 and Q1.
Yeah. No. When you divide this into the Q3 plus Q1, then we are calculating the fraction of the
middle class. Yeah. So these are some of the measures that these these developmental bodies use to get. Companies don't use them much. So this not used in very micro studies, but in more macro type of studies. When we study the columns of aggregated consumption, aggregated saving, aggregated investment, aggregated consumption of some goods, let's say the food items aggregate, luxury items aggregate, World Bank type of studies, they use it quite often. Yeah, I haven't seen any financial studies where, or the firm level study, or maybe you may be interested in knowing what fraction of your customers are in the middle class, upper class, or low class. Imagine, that's a very good example. Imagine that you have been making some advertisement campaign in the previous years. And the way your advertisement are appearing in the TV channels and different channels, it looks that you are selling the products and services to a very classy section of society. But when you collect the data and you calculate these quartiles and the difference between the quartiles, you find that the bulk of your customers are either in the lower middle income or in the lower income. And then you summon your marketing people. Hey guys, before I sack you, I want to know who was the guide who was telling you this thing that make these kind of advertisement, where the middle income touch is missing, where nothing is said about the lower class, and you are making those advertisements short and very, Bahamas, and where not very luxurious type of advertisement you're making. Your marketing campaign is always aiming rich people. They only are 10% of our customers. 90% of our customers are in this range. And then they say, who told you? Well, look at the statistics. We calculated the quartile range, and we found out that this is the situation. See my point? So these are the things which we use to make to substantiate or to support our arguments. That this is the argument which can be supported with this statistics. Okay, even though we say that there are lies, there are damn lies, and then there are statistics. But that's a very critical view. But of course, we use statistics, we make use of them, we analyze them, and they are very useful tools to at least. I'm not saying that you just believe them as they are. It's very important to understand the context, the story behind those numbers is very important. So the narrative part, this is why when people like Neil or Sophia or Ivan, when they do thesis with me, I always tell them that, remember, calculation of statistics is only 1/3 of the whole job. Remaining 1/3, the next 1/3 is how you explain those numbers in the sentence form. What lesson, how you decode those numbers into a narrative. Number 3, and then remaining 1, how you sell that narrative that people start believing you. And that is called inference. Calculation, 1/3, interpretation, next 1/3, and inference, the final 1/3. So in the whole, I think I told you this thing also, that in the quantitative research, 2/3 is not about numbers. Only 1/3 is about numbers, basically. This is why this course is not quantitative methods. Otherwise, if it's a method, I would not care much about the storytelling. But why I'm telling you so many narratives, so many stories, because in the quantitative research, the narrative is very important. Does it make sense? Good. Maybe I give you some time, and maybe Daniil can be my assistant today. I will not pay you. I'll pay you in kind. Yeah, as usual. So maybe you can play with the numbers by yourself. So you have the data. The data is available. You have the data should be in the SPSS workspace. And now if you want to do some experimentation by yourself, you can sometime.
Okay, standard by variation was about.
Yeah. Sometimes you are interested in knowing which side the data is varying. Then you are more interested in standard deviation. But sometimes you are only interested in the extent of variation, but not whether this side of the data is varying or that side the data is varying. So you are only interested in the deviation per se, not on the direction of deviation. Then variance is more important. But if you want to see the variation, but also the direction of the variation, then standard deviation is more important than variance.
So is it like, for example, in stock markets?
Look. Yeah, you're right.
So like,
no, you're right. Yeah.
The construction companies where the stocks go like high up and then down.
Yeah.
And then you can use the variance to like decide that how risky it actually is. So
yeah.
So it's not like a flat. You can't really sort of like predict that.
Yeah. Yes and no, both. Yes, because if the stock is performing above the average, that's not a problem. The problem is if it is performing on the one side, the low side. It means that in this case, you are not only interested in the variation per se, but you're also worrying about certain type of variation. Look, if the average stock return of Nokia is 2% and you get 6%, is it a problem? It's not a problem, but the problem if it's a minus 4%. So if 2% is the average and there is a minus 4%, that's the one side of variation which is causing the problem. So we are more interested in the standard deviation at that time. Mhm. But if somebody making a claim, like two-tailed test, I think in the yeah, I don't want to use this term, but I just want to remind Daniil about one-tailed and two-tailed this phenomenon. If you're not really in, if any variation is causing you a trouble or maybe falsifying your claim, perhaps it's a good idea to calculate variance than standard deviation. If a company is claiming that we have some therapy or we provide some workout that a man who is 6 feet 2 inches tall, the X kilos should be the weight according to the height. We give you a commitment that in that exercise regime of 1 month, we ensure that this guy who's at a certain height would have this weight. And that weight is exactly the healthy weight of this person, okay? Neither more nor less. Your claim will be falsified if the weight is either more, either less. So you are afraid of both sides, right? You see my point? Then I think the variance is a better measure.
Because certain deviation is like squared, it cannot be negative one. Because either way, like if the variance is negative, it's going to be squared and it's going to be positive. So you're just, if you're using certain deviation, you're using like the absolute number of how much is data is varying between each other. But if you're using variance, you can check like if the variance is negative, like data is underperforming like for somewhere. Like,
look at this case. This was the mean and this was the standard deviation. It can be mean plus standard deviation. It can be mean minus standard deviation. Right? Again, if a team score more goal than the average expected, it's not a problem, right? The problem is the less goal, right? So again, in this case, this is a problem, not this the problem. So in this case, I think more appropriate is to calculate standard deviation. Because as Daniil said, this standard deviation can be negative also. No, I don't know why. Because when you take a square root, it can be plus and minus. Look, try to understand. Variance is the square of standard deviation.
oh, yeah, sorry.
And standard deviation is the square root of variance. Look, 3 times 3 is 9. 3 square is 9. Plus 9. But minus 3 square is also plus 9. So when you square or when you find the variance, then you are not worried about this side or this side. Then you are worried about the absolute size of the variability. I would say it's not a bad idea still to use standard deviation, but if you want to have more rigorous direction-less variation, then go for variance. But if you want, if it is very important for you to consider the upside or downside, then you need to consider the standard deviation more. Sometimes your claim is falsified with a larger value, and sometimes your claim is falsified by the lower value. A company is claiming that this medicine would bring the weight down. You know, I'm giving this example because these days it's very much in fashion. This medicine you consume and the weight would go down. You lose 10% weight in 1 month.
Use that time as giving you like hints that where should you sort of like invest in stocks. And if they have like a high variance, then it's basically sort of like telling.
I want to show you something that today in our analysis so far, we have two views of SPSS. One is the data view, which is the input data and the variable view. And then we also have this another window where we have the results, the output. Now, the thing is that at some stage, you'll be interested in saving the output. The question is, where do we save it? Or in what format we save it? You're done descriptive. Now you have to write something based on it. And you want that I need to save, but maybe I save in Excel. Well, there is a way. You can save them one by one, or there's an easy way you can do is that you can export. You can export. The one way is that you can see here, this thing is very important. All or all visible or all selected. Sometimes you only want to select or save what is visible in the screen, right? But I'm going to do for all, all means all. So including the graphs, we made many graphs also. So the idea is that we save it in Excel, but if there's a graph that we save in this PNG thing, and change options, where do we save them? Well, I created some. Well, we can create a new one. I can create a file, maybe in downloads or maybe in my documents. Let's try with the documents, or maybe desktop. And I call it output, just output. And file name is output. It's on my desktop, and I save it. And remember I'm exporting it, okay? So then I can simply click OK. Just OK. It's exporting all the statistics. And now when I go to the desktop, there should be a file called output. Remember, you have to create the file first. And when you open this file, it saves all your statistics, all the calculation that you've done so far. It also shows you the graphs. So all the output that we saved today is showing up here. You see your point? So it's very easy. And I think the export function can take everything in the one go. No, in Excel. So yeah, because the problem would be that it's always save your file in Excel first, because you can make some changes. So first of all, you create a file. Okay, let's do this way. That you want to save something in the output.
Yes.
Okay, desktop. Let it be desktop. All right. And I think then you just click OK. No, let's do. I would suggest you that. Well, we can experiment with Word also, but let's say the Excel. This one. Which one is the new one? Yeah, maybe this. Maybe this one. Yeah, it's fine. And these will be J, E, G, whatever. And now I think if you. Well, look, they also came in the Word.
For me, it's not the first one that I say.
So, this looks nice actually. Fine. You okay? All right. Let's move on Let's move on to the next level. We have a new concept, which I make sure I recorded. Yeah. So I think I was recording. So the next concept that we shall be discussing is the concept of correlation. And we'll be interested in calculating the correlation between two variables at a time. The concept of correlation is very interesting. First of all, if you look at the whole analysis that we have done today, you will find that we analyzed one variable at a time. Like, for example, when you say the mean of crime rate is 0.73, for example, it's only the mean of crime rate. There's no overlap of crime rate with something else. When you say the standard deviation of crime rate is this much, it is the standard deviation of the crime rate. There's no other variable involved. So we were treating one variable at a time. So basically each column here, each column here, each column is talking about only one variable, second variable, third variable, and so on and so forth. Process-wise, we can give a combined command in SPSS, but SPSS is also very particular that all the numbers are in one column separately under each heading. But in reality, there can be interaction between two variables. Like, for example, you may say that historically, the taller husbands have taller wives. So you can say that, there's one variable is the height of the husbands, and then the pair, for example, husband A, I won't say ex-husband, I will say husband A, husband A has a wife. So there's a height of husband A, and opposite to height of husband A, there's a height of his wife. Then husband B, height, next column, in a pair, his wife's height, and so on and so forth. We can have 100,000 of people. And then we want to find that since we have two columns now, height of husband and height of wife, is there any correlation between them so that we can prove or disprove that the taller husbands have taller wives and shorter husbands have shorter wives? Or is any relationship, is any association that rich people have intelligent children? So for instance, we take the monthly salary, or let's say yearly salary of one family, one column, family A, family B, family C, family 3. And then one child, or maybe and then we find the grades of the overall combined percentage marks of their, let's say one child, highest, but let's say the eldest child, basically. So we have 1,000 of families data, and then we have the eldest child's grades data. Or let's say we have a study which says, or we have in theory, or we want to test that, is it so that the income of the family have an impact on the children's intelligence separately? So let's say we find out the family income, the yearly, one column, cross section, different families for the same year. And then we also find, let's say, we only studied the family with 2 kids, okay? So one kid marks, second kid marks. So there's a pair. Family income in the first cell, parallel cell, eldest child's marks, The other one is the youngest child's marks. And thus we collect the data of, and then we want to find out that is it so that there is a correlation between the marks secured by the eldest child with the family income and the marks secured by the youngest kid with the family income. So here we talk about two variables. Similarly, we can also be interested in knowing that is it so that more you spend on advertisement, more is the sales growth. And then we see for each firm their last previous year's data of advertisement and sales, and then we take the second company, third company, fourth company. So we can have multiple companies, multiple years. Remember the girl, she raised this point that can we have the multiple firms and for the multiple years, and I use the phrase pooled data or panel data. We can have a panel data. And then we want to find out that is any correlation between, is any association between the two. Is it so that we are spending too much money on advertisement, but the revenue is not picking up? So there is no, something is wrong. Whether advertisement is not needed for the future, or maybe we're not doing the right type of advertisement. We can also see in the reality that more you spend on education, the city council, lesser is the crime rate. I come back to the crime example again. So there is negative correlation between the two. We expect in theory a negative correlation. And then we, like we did today, we take the data of education spendings or whatever by the city council of the big cities, you know, whatever. And then we take the crime rate and we want to find out is any correlation to them. So basically, we want to do this way, this type of exercise that that is there any, we use the phrase correlation measures the degree and direction of the association between two or more variables. Degree, what level of association between the two? Like for example, if we measure the correlation and it comes to be 0.25, it means that when one correlation, when one variable's value increase by 1%, the other correlations, the other variable's value increase by 0.25%. That is called degree. Direction. Is it a positive direction or a negative direction? In case of spending on advertisement and sales revenue increase, sales revenue, what type of correlation do you expect between them? Positive or negative? Positive, because you expect that more you spend on advertisement, more sales revenue will go up, right? And then this is a positive correlation. This is called direction of correlation. Another direction could be negative. What type of correlation you expect between the education spendings and the crime rate? Negative. So it means that we are expecting the degree, there should be some measure and direction. The question is, how do we do it? Well, the direction of the correlation could be positive. Direction of the correlation could be negative. If you take one variable on the x-axis and the other variable on the y-axis, and you plot their joint values, okay? When you plot, like x value is plotted here, the y value, like for example, I can say that the age of husband A is here, and the wife of and the height of husband A is here, and the height of wife A is here. The height of husband B is here, and the height of wife B is here, right? And when we plot them, they all are falling exactly on the straight line. We can actually form a straight line by joining the 2 points. You see my point? This is called perfect positive correlation. It's perfect and it's positive. And the value of the correlation will be exactly +1. And if we take X and Y as a crime rate and the education spending, and we find that exactly their points fall like this, straight line negative. But there's no dispersion. Remember the dispersion, scatterness? There's no scatterness at all. There's no scatterness at all. Then this correlation is called perfect but negative. And the value of the correlation would be -1. It means that the value of the correlation between X and Y variable is less than or equal to 1, but at the same time, more than and equal to -1. It means the value of the correlation, either side, whether negative or positive, must be 1 or below 1. If you incidentally find out the value of the correlation 1.23, you don't need to check. It's a mistake straight away. It can never be 1 on either side. So the +1 is the perfect positive correlation, and -1 is the perfect negative correlation. If we again continue with the positive and negative side, if you plot the values, look, we will not plot actually. I'm just telling you the theory, okay? If you have the X and Y, the age, the height of husband and the height of wife, the corresponding, yeah, and the trend is positive, but you know what? Still, some points are here and here, here and here, not exactly, but not too far either of the straight line. Then it's a positive correlation, but it's not perfect, right? Then we call it high correlation, high positive correlation, right? And here the rule of thumb is that if the correlation R is less than 1, yeah, but the correlation is, let's say, more than 0.75, this falls in the category of high correlation. It's like a band, like a width, less than +1, but more than 0.75. Then we say, it's just a matter of judgment that we say, oh, it's called high correlation if it is between 1 and 0.75. On the other side, you have X and Y, and the points are there, but not exactly on the straight line. When you draw the straight line, it's negative, it's downwards, but there is some scatterness, but very tolerable scatterness. Then the correlation is negative for sure, but high correlation, right? Negative, we call it negative, but high correlation. And what is the limit? The limit is that the correlation, this is very difficult to say when it's a negative more or less. So the correlation is less than no, I'm saying that the correlation is less than it's so confusing. Let me do it. The correlation is more than -1, yeah, Because if it is 0.99 negative, it's more than -1. But the correlation is less than -0.75. Or did I say other way around?
I guess it's still right, yeah.
Huh?
I guess it's still right.
Yeah, because
Higher.
yeah, because try to understand, if the correlation is 0.80, yeah, we are right. It's true. For the negative, the position, the sign change, right? Basically, yeah. Because if it is 0.80, 0.80 negative is more than -1, but 0.80 negative is less than 0.75. Yeah. So remember, forget about sign, but remember the range that it's between 1 and 0.75. If it is negative, it's high negative. If it is positive, it's high positive. Then we move on again between plus and minus, positive and negative. If we plot the numbers, but this time scatterness is more. Again, remember, you will not do it. I'm just teaching theory. But this time scatterness is getting a bit more. But it's still not too much. Then we call it moderate or medium positive correlation. The medium or the moderate positive correlation is that the correlation is less than or equal to 0.75, but correlation is certainly more than 0.25. Learning from the previous lesson, previous slide, we keep it same. So this time you plot, it's negative, but the spread is more than before. So sorry about it, but you know what I mean, what I'm trying to say. So the sign would be this side, RXY, with a minus sign, and this would be like this. So this would be this would be more than. So I need to use the eraser. So and then draw 0.75. Next one, needless to say, if the spread becomes even more, but the correlation number is more than is less than 0.25, then the correlation is called low positive, or if it this side is low negative correlation. So if the range is between 0 is more than 0, but maybe equal to or below 0.25, then we call it low positive correlation, and same way we can modify our interpretation on the negative side. So there can be perfect correlation, +1 or -1, whichever, negative or positive. It can be a high correlation. The range is between 1 to 0.75. It can, again, plus minus. It can be moderate or medium correlation. This time the range is between 0.25 and 0.75, depending upon positive, negative. And if the correlation is below 0.25 but more than 0, then we call it low correlation. So we have perfect correlation, high correlation, we have moderate correlation, and we have low correlation, right? Is it? So you understand? But remember, one thing is very important to get. We are not analyzing the cause and effect relationship yet. We're not saying that this causes this. Look, we are having the husband's height and the wife's height. We're not saying that the husband's height is causing wife's height or something. We're not saying who's cause and who's effect. We're just seeing that if the two variables, how far they move together and to what extent. So what is the degree of their association and what is the direction of their association? We're not studying cause and effect relationship, who is causing who. That will be in regression. So in correlation, we only study the association between the two variables. We can do more, but we do pairwise, the pair two at a time, X, Y, because we have this problem of dimension. We can't show Z, axis. So X, Y is the most acceptable form of correlation. Yep.
Because the no correlation included in the medium.
In the
medium correlation.
No, the medium is between 0.25. Well, actually, I can draw it. It's easy. Otherwise, it'll be confusing. So we have positive and negative. We draw X and Y. This time, even though the overall trend is this, but now the correlation, the numbers are scattered even more. There's more dispersion or more standard deviation. Actually, the standard deviation is very much linked with correlation. High standard deviation causes low correlation, right? More scatterness. So the correlation would be this time RXY is equal to or below 0.25, but it's more than 0. Because if it becomes 0, then it becomes no correlation. No correlation means 0. There's no correlation. But that's not the situation. Sorry, I drew wrongly. This should be going upwards, but scatterness is more. And here we plot XY. The overall association seems to be falling, but the scatterness spread is huge. In this case, we can say that the correlation low negative correlation. Does it make sense? And if the correlation happens to be 0, then we say there's no correlation. So there is perfect, there is high, there is moderate, there's low, no. And then we go in other territory, negative correlation. Then comes low negative, moderate negative, high negative, perfect negative.
The moderate comes from 0.25 to
0.75. Yeah.
0.75.
Yeah.
Okay. Because I remember, maybe I mixed up with something, but I remember there was a degradation of the 0.25 to 0.5.
No, never. The only difference between what I'm saying and some researchers, they don't take 0.75 as a cutoff point. They take 0.80 as a cutoff point. But I think it's good that we have 25, 75 like this. It's easy. Yeah. All right. Now we move to calculating correlation in SPSS is the easiest thing. I think even easier than descriptive statistics, because you have nearly nothing to click, basically. We don't need to go here and there too far. Our data in SPSS is here. Our input data is here. As I told you before, that the bulk of the times we'll be using the analyze function. Now, I need your attention. Analyze. Yeah. Look, it's so simple. What concept we are studying? Correlation, and it says correlate. And then when I was drawing X and Y, how many variables we were studying at a time? 2, and 2 is called bi, mono, bi, tri, tetra, all these things. Bivariate, So you know what to click: analyze, correlate, bivariate. And once again, this dugout appears. Dugout means we will choose now which variable we want to analyze. Not a bad idea to select all of them by the shift function. With the arrow down, you can choose all of them and then move them to the activity area, the football pitch. By default, we have Pearson's correlation. Carl Pearson has been a very famous statistician who gave this idea of correlation. If you
yeah, if you, for example, select first one, and now that's this thingy, and the arrowhead down, and well, you can take combine because we have some additional variables also. Put them. You may return those because we just made those fake variables. Remember, they combined because otherwise your result may differ from the others. So we send it back. Yeah. So now you have exactly the same variable which I have.
Yeah.
Even though I'm using different spreadsheet, but
yeah. So we do nothing in this page, except that we choose. Well, it's by default. We choose the variables, right? Options. Do we need any options? No. Nothing else. Nothing else. So this is the most carefree analysis. We just choose the variables in the activity area from dugout to activity. Pearson is chosen by default. Two-tailed test is chosen by default. I don't think there's need to make any change. Just click OK. Yeah. You see that? Do you get this thingy? Huh? Oh, yeah. You get this? Yeah, this type of table. All right. You can see that there's a 1, 1, 1, 1, 1 here in the diagonal. Can you see that? The reason is that the correlation, the same variable is on the horizontal axis and also in the vertical axis. So there is a table. Obviously, the correlation between crime rate and crime rate will be 1. You know, because it's like, so it's like a matrix. So that is why we have this diagonal 1, 1, 1, 1, 1. I want to slightly draw your attention. I want to deviate your attention a little bit from this table. There is a phrase SIG. SIG. SIG stands for significance. Significance. The question is, how significant are your results? Look, if this course was statistical course, I will not care about significance. But the question is that you have the variables, you are analyzing them, you found some results, and now you want to make an interpretation based on your results. The question is that how significant, how important are your results? If the significance, look, the correlation between the crime rate and dropout density is 0.223. 0.223. It means that there is a 22.3% association between the correlation is, first of all, please tell me, is this low correlation, moderate correlation, or high correlation? Low positive correlation. The question again is not that whether it's low or high. The very important thing is that is the direction positive or negative. Now, this is like I'm telling the practitioner side that if you are a statistician, you will be very much worried about the size of the coefficient, that it's low. I don't care about low, medium, high. Now, in reality, all I care is that is the sign positive or negative? Sign is positive. So the correlation is positive. It means that more crime rate and more dropout of students from the school, they go together. It's not opposite, they go together. As I expect in theory. In theory also I expect that if people opt out of studies, they may indulge in the criminal activities, right? The question is that, is my result significant or not? Look, significant is here, what? What is the value of significance?
0.000.
Can I say 0%? Significance is 0%. Wait a sec. The significance basically here is telling that I can say with 100% confidence that this association is really meaningful and is true. We have an expression here. I think it's time that I should draw it so that you see what I mean to say. Share. If the level of significance of a finding in econometric or quantitative research is 0%, then the level of confidence, the confidence means how confidently you can argue your results, is 1 minus 0%, or 100 minus 0%, if you can say, because we're talking about percentage. You can say with 100% of confidence that your finding is great. Now what we concluded from this finding, that the correlation between the crime rate and the dropout intensity is positive relationship, and this we can say with 100% of confidence that our finding is true. If it happens that the level of significance is 1%, here 1% means there's a 1% possibility of error. You know, there's a 1% error in the report analysis. Therefore, you can say, what is 100 minus 1%? 90. You can say with 99% of confidence that your finding is true. If the significance is 5%, now you know it's 95% confidence. You will be wondering how much we can tolerate. What can be the maximum level of significance? In other words, what can be the minimum level of confidence to be accepted? Some researchers say it's 5% is the limit. No more than 5%. Imagine the correlation between the two variables, crime rate and association, the dropout is still 0.223. But when we see the level of significance, it comes out to be 0.0613. I'm just cooking up the numbers, which means 6.1%, right? Which is more than 5%. 6% means now your level of confidence has gone down to 94%. You with me? Some people say that 5% is the limit. If the significance level is more than 5%, like in this case, 6.13, remember, they never show significance in percentage. They show in the coefficient. You have to make adjustment that 0.06 means 6%, yeah? because we move 2 decimal points to the left when we convert coefficient to percentage. Okay. 0.613 is not a percentage, it's a coefficient. So basically it means 6.13 percentage, which is certainly more than 5%. And thus, there is a correlation, but we don't accept it because our level of confidence has fallen below 95%. But I would say that most of the researchers, their tolerance zone is 10%. See my point? It means the minimum accepted level of confidence is 90%. If your significance is more than 10%, then that finding, there will be some coefficient value, but that value is not enough to believe. I always give the example that imagine if I'm a cop, I'm a head cop in the police, and you are my inspectors. And there have been some criminal activities, and I depute you, guys, go and you investigate one case, you investigate one case. And the law says that the person is innocent until proved guilty. You have shortlisted that these people could be potential criminals, right? You make you come with a decision. And let's say Ivan comes to me and he says that in my opinion, the person is guilty. Let's arrest him. He's asking me that I should sign the warrant so that he can go and arrest. And then we say, Ivan, let's have a meeting. Let's before it's a very big decision to arrest somebody. What is the level of error in your report? Be fair to me. First he says, oh yeah, I think it looks that the fingerprint are not fully matching. Some tips match, and then at the crime scene there was a foot mark, but it seems that the shoe size of this guy is smaller than the mark. All right. What else? I find that there are the report is good, or not crap, it's very good, but there are some gaps and holes in the report. And I say that, let's say, Ivan, let's make a decision. Can you say with minimum 90% of confidence or with 10% possibility of error that this guy is criminal, he's guilty? And then he says, no, I think it's the level of the error potential is more than 10%. Hence, the confidence of this report is less than 90%. Then even though there are some leads mean there is a calculation, there's some value number, I will not believe it. But then for some of you, when you make your case investigation and you say, Shab, okay, 1% error, 2% error, but you know what? I assure you, error is not more than 2% in this case. And they go, well, let's have a chit chat. And I check your report and I find that, yes, you're right. Okay, then I say, sign, go and arrest this guy and put him behind the bars right now. That is a significance. That is the relevance of level of significance, means how much error is permissible, and level of confidence after discounting for the likely error, how confident you are to believe in that. Does it make sense? So remember, in reality, we don't care much about the degree of significance in the empirical research. We care about the direction and we care about the significance. Let's see. This is a correlation matrix. Look, there is a correlation between poverty and the crime rate. The theory says that often poverty compels people to commit crimes. And we believe it. But when we see our finding, it's positive, it means that poorer people, poverty and crime rate is associated. But when you see the significance level, 0.638, 63.8% error chance. Should I accept this result?
Why is it so high?
Don't know. This is the data is speaking. We are not saying that the theory which says that there is a crime rate and poverty have some association. We are saying that our data is not according to the theoretical. So we don't blame the theory, because maybe in when you analyze, this can be true. But in my case, the results are not corresponding to the theory. And we say that even though there is some calculation existing, look, if we were calculation obsessed, we will say, hey, the correlation between crime rate and poverty is 0.20, thus it's low positive correlation. But when we see as an econometrician, when we see as researchers, we find that the level of significance is absolutely unacceptable. There is a 63.8% chance of errors. We don't accept this result. We show it, but we don't accept it. I mean, we will not throw it out of our data. If you see, we show it, but we also make a comment in the when we write our 4th chapter of results that there's no evidence that there is any association between poverty and crime rate. Look, I think I told you on the very first day that when you prove something, it's a finding. But when you disprove something, or when you are not able to prove something, it's also a finding. Because all the theories, as you raise the point, the theories is very strong, is saying that there is a association. But our empirics are not supporting the theory. What can we do? Maybe in a different setting, in a different research, in a different data, in a different year, in a different set of variables, maybe it holds. But in this case, it's not holding. Like in your case, we had this hypothetical square variable, remember? Maybe it works. But the existing set, it doesn't work of variables. Same way, you can see that the poverty ratio and dropout density is not, even though it's positive correlation, but it's a huge amount of error. The correlation between alcohol consumption and poverty is negative and significant. Look, this is so good, such an interesting result. We often believe that poverty leads to, or poverty sometimes causes, if it is a cause, leads people to alcoholism. But we find that actually it's opposite. Alcohol consumption and poverty are negatively correlated. I mean, those people who are more alcoholic are actually not poor. And those who are poor are actually consuming less alcohol. And look, the significance is how much? Approximately 0. Yeah. So this result is acceptable or not acceptable? We accept it. So this is how we read the results. This is how we read the result. That, again, I repeat, if I were you, I'm telling you not as a teacher, but as a researcher, that I don't really care about the degree or the size of the calculation. Is a 0.39 or 0.89, whatever. All I care is that, is sign positive or negative? And if it is true, is it acceptable or not acceptable? Is it significant or not significant? If it is significant, which means confidence, we accept it, otherwise we don't accept it. Is any bottom line result, which is very close to, like this is 15.5%, not too bad, but we don't accept it because it's more than 10%. Yeah. Otherwise, we have very clear, this is also fine, 13.7. We don't accept it, even though it's very close to 10%, 13.7, but we don't accept it because it's more than 10%. So we don't, even though it's negative, whatever it is, we don't care. So this is how basically we interpret the results. So we are basically saying that there is a correlation existing, but this correlation is so insignificant that we can't really accept it and we can't act upon it. See my point? And the same thing, like I gave you the example of this cop giving the cases to the inspectors. The same thing you can also do in the business settings, that there is a correlation between advertisement and selling, and it's positive, but significance level or the error level is more than 10%. Then we say that, even though there is a positivity between the two variables, but it's not enough to accept it. Thus, we don't carry on our marketing campaign now. So we take a decision. Then what do we next? Then we start thinking. Then it comes to strategic planning and strategic management. So all these things are interconnected. It's easy to calculate correlation. And if you know the theory that it's a degree and direction, and the way I plotted the range 0.25, 0.75, 1, what has been the highest correlation, if I can quickly see? The highest correlation so far is 0.31 something. Oh no, there's 0.67. So this is like a moderate positive correlation, 0.67. 0.67 is between 0.75 and 0.25, right? And positive, moderate positive. Is anything else interesting values? Here, yeah. 77.4 correlation is. So there is no, that is significant level. I'm sorry. So you need to be careful that, yeah. Okay. So that's the thing which I thought I should discuss with you. Yeah.
There was one correlation between population density and dropout density, and it was completely one.
Say again, dropout?
Dropout density and population density.
Where is population?
Population density is the lowest. Down.
Ah, okay. Where is that? This one, yeah. Oh, this is one.
Yeah.
One. Yeah. So it's not just in the diagonal, but it's also. So it's a very rarely we see it's perfect positive correlation. And it's 100, and this you can say with 100% confidence that this correlation. So there is, if you plot population density and this dropout density, they will fall exactly on the same line, all the way. No variation, nothing changes. Fantastic, very rare. Well done. It's a very rare result that you have. Yeah, it could be.
Population density with a dropout density.
Well, first of all, this is fake data. I was thinking that how many people per square kilometer live, population density mean there are some areas where more people per area live, and dropout density means people leave the school. So in a way, it's theoretically true. Those cities where there's a lot of population pressure, the area is so congested. Often there people don't complete their school, and because there's more population, there's a high chance that they meet more people with bad company and they drop out from the school. No. The idea here is that those areas, let's put it this way, those areas where population is less, then people don't drop out. They complete the studies. Maybe they have no other option but to go to school. But here, I can build up an argument that maybe because of more population, parents are working, kids go to school, and the kids don't go to school actually. They go elsewhere, and then they fall in the bad company, and eventually they are thrown out of school, and there is teachers don't care because so much of population pressure and so on and so forth. Yeah. So eventually this happened that more dropout in case there is a more population. But it's one, right? I'm now getting intrigued. If we have the graph, I'm just thinking to my heart say that we should experiment. That's very interesting case. If I have a graph and I have this chart builder, I'm now using another function. And which were these two variables? We had population density. Yeah. So if we, why? Because my window is absolutely. Sorry, just a sec. Now I share the screen. So if I want to draw a graphic, and if I take the line, and I take this one, and on the, doesn't matter who comes on the, so the variable was dropout density. So if I put it here, and the other one was
Population density.
Population density. Or did I choose a wrong graph? If I take the scatter, maybe. Yeah, this is something. But exactly as per the graphics, they're not falling on the same point. But the calculation is showing that it's a +1. Yeah. If it is based, honestly speaking, if it is based on the graphics, first of all, graphics are only displaying something, but they're not very rigorous. When you are calculating it, the correlation, that is more rigorous because it has gone through the entire process, you know. If I have to make a decision purely based on the graphic, I will not even call it high correlation, let alone perfect. It's a positive, but it's a kind of moderate positive something, you know, not more than that. Yeah, so it's a bit different. But if there is a two opposite kind of findings, I would trust the coefficient. And because they involve the concept of significance, which is the hallmark, which is the backbone of the entire quantitative research, rather than looking at the graphics. I don't know why it looks like this. But this is all basically I want to discuss with you today. And as we discussed before, that you can save this finding and you can save your data so that we start exactly where we left tomorrow. Yeah. Tomorrow we will be doing correlational analysis, regression, and we will do multiple types of regression, but the core philosophy would be same. And we will also do something else. I will decide tomorrow what to do. Yeah. But I can't say right now what we'll do, but maybe regression plus one more topic, and that would be everything.